This is the third in a series of screencasts on the subject of acid and bases for the module CHE10063. So today we're going to talk about the estimation of pH and how we can relate it to the pKa, okay? And in particular, we're going to focus on the use of weak acids, so estimated pH of weak acids, okay? So we'll start by considering something that you should already know, which is how we can estimate the pH of a strong acid. Okay, so we're going to start with the question, what is the pH of a solution of 0.1 molar HCl? Okay, and so in order to do that, what we have to do is we have to just remember the equation for pH. So pH is equal to minus log to the base 10 of the concentration of H3O plus. So that is, and therefore we can just put the concentration in here. So we say minus log to the base 10 of 0.1. Yeah. And again, in this case, we have to divide, strictly, we have to divide the concentration by the units. So because you can never take a log of something that has a unit. But again, the laws of logarithms, we're going to cover that in Maths for Chemistry screencast. Anyway, it's minus log to the base 10 of 0.1, which is equal to 1. Okay, if you put that into your calculator. Okay, so the pH is equal to 1 when you have a concentration of 0.1. And that's also the same as saying if the pH is equal to 1, then the concentration of, so we can say if pH is equal to 1, then the concentration of H3O plus is equal to 10 to the minus 1, which is 0.1 molar. Yeah, 10 to the minus 1 because it's 10 to the minus pH. So if you just remember the relationship, concentration of H3O plus is equal to 10 to the minus pH. And that's another way of writing the equation with the log in it. Okay, so we get the same results, but anyway, you should be able to do that, and you can do that if it's a strong acid. And the reason you can do that because it's strong acid is because strong acid are approximately 100% dissociated. So the vast majority of the acid that's in there is existing as a dissociated species. So essentially H3O plus and A minus. Yeah, so it's on the right hand side of the equilibrium. But for weak acids, now we have a scenario where our equilibrium lies on the left and there's not as much dissociation. So therefore we cannot say that all of the acid is present and has dissociated to give us H3O plus, which is what we said in the past. We now need to take into account the equilibrium constant. Okay, and we need to take that into account. If we know the equilibrium constant, so that means we know where the position of the equilibrium is, we can still calculate the pH, but we must take that into account. Okay, so if the acid concentration isn't too low, we can make this approximation, okay, which is essentially that the bottom here, the concentration at equilibrium of our undissociated species is very close or the same as, or nearly the same as, the concentration that we made up in the first place. In other words, we're making the approximation that actually, very little of the acid has dissociated, okay? And if we do that, we can rewrite the equilibrium equation as, let's do it in a better color. Ka is equal to concentration of H3O plus concentration of A minus over concentration of HA initial. Yeah, that's the first thing we do. The next thing we can do is we can say that the concentration of A minus is equal to the concentration of H3O plus. Okay, and that's assuming that there's no buffer. So if the question doesn't say there's any buffer, we can assume there's no buffer. So in that case, we could then say that then gives us Ka is equal to H3O plus squared over concentration of HA initial. And now we've got an expression for our concentration of H3O plus, okay? And obviously once you've got the concentration of H3O plus, you can calculate the pH, just by saying minus log to the base 10 of concentration of H3O plus is equal to pH, okay? So that the expression for H3O plus is this. Is equal to the square root of Ka times by concentration of HA initial. Okay, and that's that. And there's a key point here, which is that you need to know how to get the equation that I've underlined. All right. So let's just sort of go through an example where we're using this equation. This is hopefully fairly straightforward. We can write down the equation first and foremost. So concentration of H2O plus is equal to the square root of Ka times by HA initial. And here we're going to see what that HA initial actually is. Yeah. So the pH of that solution. So this is this concentration, 34 millimolar, is HA initial. Okay, because that's the concentration you made up in the first place. It doesn't say anything about equilibrium concentrations. Okay, so we can say that. Yeah, so that's that. The pKa we need to convert first. So we're writing down our equation. We need to say Ka is equal to 10 to the minus 4.79. Yeah, and you can work that out and what that is equal to, and it's equal to 1.62 times 10 to the minus 5. But you can also just keep that in the calculator like that. Incidentally, 1.62 times 10 to the minus 5, of course it's 1.62 something 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 in terms of the number of sig figs. So we should keep the full number in the calculator whilst we're doing the question, because otherwise we're introducing error. So it's 1.62 ... Okay. So we've already said that's equal to 34 millimolar, which is the same as writing 34 times by 10 to the minus 3 molar. Yeah. Now here is where the unit tracking is appalling, because in order for this expression to work and to give us molar, as a result, Ka actually has to have units, doesn't it? So, once again, I said already that unit tracking during acids and bases is a bit annoying, and that's basically because all of these are effectively divided by molar, and so there aren't actually any units. Okay, but generally speaking, we just need to remember that every time we have a concentration, it's going to be given in molar, but we need to make sure that we get rid of something like the prefixes like milli here. Okay, in order for that to work. But anyway, if we put this all into the equation, we can say concentration of H2O plus is equal to the square root of 34 times by 10 to the minus 3. And I'm going to just ignore the units for now. And I know this is different to what we've told you elsewhere, but I think it's just easier in this case of this course. Okay, and that's, we can also say there aren't any units because we divided them all by the units anyway, right? And so if you put that into your calculator, you end up with 7.4 molar times 10 to the minus 4 molar, sorry. Okay, and then of course pH is equal to minus log to the base 10 concentration of H2O plus, and that is equal to 3.1. Okay, and we can give that to two significant figures because our concentration had two significant figures at the start. And again, you'll get some opportunity to practice using this equation in the associated quiz. Okay, so to sort of finish this topic, we're going to talk about an equation that does use a buffer. Okay, so the Henderson-Hasselback equation is one that is typically used to calculate the pH of a solution containing a buffer. Okay, and it relates pH, pKa, and the concentrations of the dissociated and undissociated species. So this would be the conjugate base of the acid, and this is the undissociated acid. Yeah. Key point actually here is that if these two are equal, if A minus and AH are equal, then 1 divided by the other is equal to 1, and so therefore log to the base 10 of 1 is equal to 0, and in that situation pH would equal pKa. Okay, and that's what this says here. So in that case you have an acid that's 50% dissociated. So if your pH and your pKa are roughly the same, your acid is approximately 50% dissociated. Okay. Key point when you're actually using the Henderson-Hasselback equation, as we will try a bit later, is that we normally make the same approximation as we've already made here, which is that our concentration of our undissociated acid species is equal to the initial concentration, and that our Concentration, and this is a bit different, but it's kind of the same idea, of the dissociated species is equal to the amount of buffer we put in. So, the initial thing. And, the first one we've already talked about. The reason why the concentration of A minus in the Henderson-Hasselback equation is going to be about the same as the initial concentration is because, again, we're talking about weak and acids, and they haven't dissociated very much. So the amount of A minus that's coming from the acid dissociation is relatively small compared to the amount that comes from us adding the buffer in the first place. The nice thing about Henderson-Hasselback is that you can actually derive the equation in a relatively straightforward way from the equilibrium constant. Okay, so we're going to do that here just quickly to show you, because being able to derive equations shows that you can understand where they come from. It's an important skill in physical chemistry. So I'm just going to write out the equilibrium equation here, and then we will go from there. Right, the first thing we're going to have to do is we're going to have to take logs, and that it should be fairly obvious that we're going to have to do that because obviously the Henderson-Hasselback equation that we want to get to at the end is pH is equal to pKa plus log to the base 10 of the concentration of A minus over the concentration of AH or HA, yeah, and obviously these species involve log, so P is generally equal to minus log to the base 10, isn't it? Of, in this case, pH is equal to minus log to the base 10 of concentration of H plus. So we're going to need to take logs first. So once again, we're back to logs. And again, I want to remind you that screencasts for laws of logarithms will be coming soon. So let's just take the logs. Log to the base 10 of Ka is equal to log to the base 10 of all of this stuff. Okay. Now, as I already said, there's a law of logs that says the log to the base 10 of AB is equal to log to the base 10 of A plus log to the base 10 of B. Yeah, so we can rewrite what we've just written as log to the base 10 of Ka is equal to log to the base 10 of the concentration of H3O plus, yeah, plus log to the base 10 of concentration of A minus over concentration of HA, yeah, and that, that already is giving us the same term as down here, and you can see where the other two are going to come from, can't you? Because now what we need to do is multiply both sides by minus 1, so times by minus 1, and we're going to get minus log to the base, oopsie daisy, sorry, I'll just rub that out because that's not very pretty. Log to the base 10 of Ka is equal to minus log to the base 10 of concentration of H3O plus minus, log to the base 10 of the concentration of A minus over concentration of AH. Okay, now we can then say this is pKa, this is pH, and we just need to do a bit of arrangement and we end up there. But first and foremost, we're just going to write this out. So it's pKa is equal to pH minus log to the base 10 concentration of A minus over concentration of AH. And of course, if you basically add the log to the base 10 of A minus over AH to both sides, you'll cancel it from the right hand side and you'll add it to the left hand side, and you'll end up with the Henderson-Hasselback equation as written here. Okay, so that would be just plus log to the base 10 of to both sides. Okay, so it's quite easy derivation, just straight from the equilibrium constant formula. Okay, to finish this screencast, I just wanted to do a quick worked example of the use of the Henderson-Hasselback equation. Okay, and so, we have the equation here and we have a sort of typical question. It talks about a buffer solution, it gives us a pH, and we have a solution of acid that we've already got, and we need to work out how much sodium acetate we need to add to the solution, and we've got a pKa. So of course, one of the things we're going to do, what we need to work out is the amount of sodium acetate. Now, acetate, that's going to be A minus, isn't it? Okay, so we need to work out the concentration of A minus. So we need to rearrange the equation first and foremost. So let's do that first. So the first thing we're going to do is we're going to put pKa onto the other side. So we can say pH minus pKa is equal to log to the base 10 of the concentration of A minus over concentration of AH. And then, as we've said before, we can sort of, convert these by writing out the following. Okay, so we can say, okay, concentration of A minus over concentration of AH is equal to 10 to the pH minus pKa. And then we can say, in that case, concentration of A minus is equal to concentration of AH times by 10 to the pH minus pKa. Okay, and if we do that, what we get, and we can now just put the numbers in. So we know that pH is equal to 5.27. We know that the pKa is 4.75. So we can do, pH minus pKa, which is going to be 0.52. So we can say, yeah, is equal to 10 to the 0.52, sorry, not minus, 10 to the 0.52, and that's multiplied by the solution concentration, so the concentration of our acid solution, which it's not a concentration, it's a number of moles, sorry, but this could be in a liter, so that would then be a concentration, but it doesn't really matter because we want to know how many moles to add. Okay, so we've got an amount, not a concentration, so it's 10.0, and we can just leave it as 10.0, just being aware that this is then going to give us an answer in in millimole. Yeah, and then if we put that together, we can get concentration of A minus is equal to 33.1 millimole. Okay, and that sort of makes sense because 10 to the 0.5 would be the square root of 10, which is about approximately 3, isn't it? So it makes sense that 10 multiplied by about 3 is going to be about 30. So that looks about right. And I've written out the units incorrectly because I've written out millimole to the minus 1. It should be millimole, shouldn't it? Yeah, and it comes from the fact that we left that as a millimole. Okay, so that's how you do that.